We will start the session in a couple of minutes. Let's let a few more people join. Okay, so let us begin. Uh, so today we shall be covering some of the very basic concepts of C++. They are pointer, structure, stack, and heap. So first, let's discuss about pointers. So pointers are a special kind of variables which store the memory address of other variables. So basically, pointers are also just another special kind of variables. They are also variables. And now, why are they called pointers? They are called pointers because they store memory addresses of other variables. By storing memory addresses, they tell us where other variables are. So they like point to other variables. That is why they are called pointers. So in a 64-bit machine, the size of a pointer will be 8 bytes, and in a 32-bit machine, it will be 4 bytes. And today, most of our laptops and all are 64-bit machines. So most probably the size of pointer will be 8 bytes. So before actually going in deep into pointers, let us discuss some syntax, some basic operators of, related to pointers. So the first operator is the address of operator. It is denoted by and, it's generally called ampersand. So when you apply this operator on a variable, you get the address of that variable. So, and let's say there is an integer variable, name it, call it y. You use ampersand y, you get the address of the memory location where that variable is present. And the second operator is the dereference operator. It's denoted by star. So this operator is applied on pointers specifically. And when this operator is applied on a pointer, you get the value of the variable which is pointed to by the pointer. As we previously discussed, pointers store some memory address, and there will be some variable present in that memory address. So when you use star, you get that variable basically, which is present at that memory address which is stored in the pointer. And let's say your variable is of type t, then your pointer will be of type t star. So let's say you have an integer variable. If you want to have an integer pointer, your integer pointer will be of type t star. Similarly, all they hold for all the built-in types, and also if t is a user-defined data type, the pointer will be of the type t star. So we shall soon discuss what user-defined data types are. So let us look at this example. Here y is an integer variable and its value is 10, and this is what the first line is. And the second line is you're declaring an integer pointer. Basically, what does this say? As we previously discussed, if your t is int, then the pointer will be of type t star. That is, here t is int, so the pointer is of type int star. Int star z is ampersand y. So as we previously discussed, ampersand is the address of operator. When you use this, you get the address of y, and basically that address is being stored in z. So that is what this means. And here the illustration is for a floating point variable. So x is a float variable and its value is 20, and p is a pointer to x. Another thing, if you notice carefully, here the star is placed along with z, the pointer, whereas here star is placed along with the data type. So it doesn't really matter. You can place it along with the variable or along with the data type or with neither of them. You can place it somewhere in between them. So basically, don't get confused about the position of star. You can place anywhere in between the pointer's name and the int or float or the type t. It can be placed anywhere. So this is an illustration of how pointers work. Here var is an integer variable, and what it's storing here is 10. So the value of var is 10 here. And this is present at a certain location in the memory, and this green colored address is the address where this is present in the memory. Now ptr is an integer pointer and it points to var. So what does ptr have? Ptr has the address of var. Now, in one of the previous slides, we have seen that pointers are special kind of variables. So basically pointers are also variables. So even they have a certain address. And this black colored thing is the address of the pointer variable. And now, what do pointers point to? Pointers point to other variables. They store the address of other variables. So since pointers are also variables, you can have a pointer which points to another pointer, since that other pointer is also a variable. So such pointers which point to other pointers are called double pointers. So if we have a pointer which stores this address, black colored one, it will basically become a double pointer. So this is here we're illustrating the double pointers. Y is an integer variable, 10. Z is again a pointer to y. We have seen this previously. Now this is A is a double pointer. A is basically a pointer to Z. So A, we are equating it to the address of Z. So basically here Z stores the address of Y is an integer variable. Similarly, A stores the address of Z since Z is also a variable. And this is how you denote a double pointer. You denote it with T star star. So again, these stars can be placed anywhere between int and A. So they can be placed along with int, they can be placed along with A, they can be placed anywhere. So don't get confused with that. So similarly, again, double pointers are also variables. So we can have a pointer which points to them. Such pointers are called triple pointers. And we can even have a pointer to triple pointer in this continuous symbol. Now, let's discuss how to dereference a pointer. So y is an integer 10. Z is again a pointer to y, same ones which we have done previously. And here we are trying to output star z. And this is the output that we get 10. So basically what is 10? 10 is the value of y. So when we dereference a pointer to y, we get the value of y. So when we dereference a variable, which is when we dereference a pointer to variable, we get the value of the variable. Okay, so what all do pointers point to? They can point to built-in data types like int and float. We have seen a good number of examples on these. They can point to user-defined data types. We shall soon look into this later. Uh, they can also point to functions. So basically, functions also have a certain space in memory, and hence they also have a certain address. And it's possible to have pointers to functions as well. So this is the syntax. You might be familiar with the syntax to declare a function. So function basically takes a few parameters and it returns a certain value. Return type is the data type of the returned value. Fn is the name of the function here. Parameters is the list of parameters that you're giving to the function. And this is how you declare a function. I'm pretty sure most of you will be familiar with this. And fptr is a function pointer. So since we want to make it point to this fn function, we should give the return type of function fn, the various parameters that the function fn takes. And in order to tell the compiler that this is the function pointer, we use star fptr and we enclose it within brackets. And how do we initialize it and make fptr point to the function? We simply equate it to fptr we simply do fptr equal to f, and we don't need to use any ampersands here. This is a bit different compared to initializing a pointer to other variables. So let us discuss a few special types of pointers. First is the uninitialized pointer. You might understand it from the name. If you just declare a pointer and leave it like that without initializing, it will be called an uninitialized pointer. So a pointer that has not been initialized to anything is called an uninitialized pointer. So when you don't initialize it, it just contains some random values. You don't know what it contains. And this is how you can have an uninitialized pointer. As you can see, you're just declaring an integer pointer Z and you're not equating it to the address of any variable. So Z contains some random values, which you don't know. It can be anything. So it always keep in mind to not use an uninitialized pointer because it can lead to unpredictable results. You don't know what's there in it, so you can't predict what happens. It might throw up an error and quit and exit, or it might still continue in the program and it might give you some unpredictable results. You don't know what happens. Now the second type of pointers are void pointers. So if you have an integer pointer, say you that can only point to integer variables. If you have a float pointer, that can only point to floating type variables. But void pointers are a special kind of pointers which can point to any type of variable. So as you can see here, a is an integer variable, but here PTR, which is a void pointer. This is the syntax. You do void star PTR. You equate it to ampersand A. Here A is an integer pointer, but still you can do this since PTR is void star. Now let's say you want to assign PTR to another integer pointer. Say PTR2. What you do is you write insta PTR2 equal to PTR and you typecast it to insta2. Tell the compiler that you're making it an integer pointer. You're just typecasting it. And the third special kind of pointers are null pointers. So null pointers do not hold the memory address of any variable. Note that this is different from uninitialized pointers. So uninitialized pointers might point to some memory addresses, but but that memory addresses which they point to, you can't predict what it is. You don't know what it is. It can point to anything. But null pointers don't point to anything at all. So this is how you declare a null pointer in star PTR equal to null PTR. We use the keyword null PTR. And arrays and pointers are pretty closely related. So now let's look at the relation between arrays and pointers. So the name of an array is a pointer to the first element of the array. So let's say you have this array of 10 elements, integer array. Here ARR is the name of array. Now what is the first element in this array? ARR 0. So ARR 0 is also an integer variable. So that also has a certain memory location, and that memory location has an address. So, and how do you get the address of ARR of the first element in the array? You apply the address of operator. You do ampersand ARR 0. So ampersand ARR 0 is identically equivalent to ARR. And ARR plus 1 is the pointer to second element. ARR plus 2 is the pointer to third element. And in general, ARR plus I is the pointer to I plus 1th element of the array. Now, what happens when you apply dereference operator on ARR plus I? Since ARR plus I is a pointer to the I plus 1th element, applying dereference operator on it gives you the I plus 1th element of the array. And what is I plus 1th element of the array? It's simply ARR square brackets I. Now, let's say we have another integer pointer called PTR, and let's say you assign ARR to PTR. So now PTR is an integer pointer, ARR is also an integer pointer, and now they are exactly equal. So now PTR and ARR become identical. So all these four are equivalent. Star PTR plus I is the I plus 1th element of the array. Then PTR is identically equivalent to ARR. So star PTR plus I is equal to star ARR plus I. Both of these are equal to PTRI, which is the I plus 1th element again. And PTRI is also equivalent to ARRI because PTR is identically equivalent to ARR. So, scan this QR code and so basically you have two sample codes here and you have to predict the output of them. So scan this QR code and answer this question. I'll give you a bit of time, 2 to 3 minutes, so you can answer the question. I'll wait for 1 more minute and let's continue. Okay, so I'm closing the voting and 3 comma 2 and 2 comma 3 is the correct answer. Now let's see why it's the correct answer. So here in the first code, program 1, um, we are passing A and B to the array. So A is 3 and B is 2. Swap A comma B. So you are passing swap 3 comma 2. So and now what does the swap function do? It takes two parameters A and B. It equates temp to A. So here your A was 3, so temp becomes 3. Now A become A, you're assigning B to A, so A becomes 2, and B again you're assigning temp to B. So B becomes 3. So but why is it not reflecting here? Why do you still get 3 comma 2? It's because the A and B which you find in the function main are different from the A and B which you find in the function swap. So when you call A comma B, you're not actually passing the original A and B, but rather you're making a copy of A and B and passing it to this function. And that copies are being assigned to new variables called again with the same name A and B, which are present in the function swap. So this A and this B are not same as this A and this B. So while doing this operation, the A and B present in the function swap are being modified. Your original A and B which were present in your original A and B which were present in the main function are not being modified. They are still remaining the same. So, and how do you actually swap them? So here what we are doing in program 2, we are passing the addresses of A and B. So swap takes two pointers, which are that which is first one is the address of A and second is the address of B. Here you're accessing these variables A and B by using their memory address. So you're not actually accessing their copies. You're able to access the original A and B. And how are you doing that? By accessing them using their addresses. So here it's basically the same thing. You use the dereference operator for the pointer and the basic swap algorithm only. Just that you're actually able to modify the A and B in main because you're passing the memory addresses of A and B. Hope this is clear. So in this is how you do if you want to modify the actual variables in a function, this is how you do it in C. There's no other way to do it in C. This is commonly termed as pass by reference. You can search it if you want. If you want to understand it in more detail, you can search it. It's called pass by reference. In C++, there's another way to do it. So that we should not be discussing here. So this is how we do it in C. This is just to illustrate the use of pointers. So let's start the new topic, structures. So previously we have seen this word called user-defined data types a few times. So structures enable us to have user-defined data types. What do? They group items of different data types together into one data type. Um, and then that data type will be a new user-defined data type. As you can see, this is the syntax. Name, you can have any name of your choice. Data type 1, data type 2, data type 3 are basically they can be any data types. They can be int, float, or they can even be another user-defined data types. The item 1, item 2, item 3 are the variables, the member variables of this structure data type. So let's look into this more. Let's look into this example for clarity. So here, the name of our structure is example. It has two variables in it. exint and exflt. Exint is an integer variable. Exflt is a float variable. So here we are declaring a new variable called str1. str1 is of type example, and so as you can see, example is being used like another data type. Let's say you want to declare an integer variable, you do int y. So similarly, here you're doing example str1. Example is literally being used like a data type here. And that is why it's called, but it's not built in, it's user defined. So that is why it's called a user defined data type. So when you do, and how do you access the exint and exflt variables present in str1? You access it using the dot operator. So when you do str1.exint, you get the exint present in str1. And here you're assigning it to 5. And similarly, when you do str1.exflt, you get the exflt present in str1, and here you're assigning it to 8.2. So there is another way to access exint and exflt. This is not the only way to do that. That is by using pointers. So as you have previously discussed, we can have pointers even to user defined data types. So we can even have a example star pointer. Example star pointer is ampersand str1. Basically, PTR is a pointer to str1. So now how do we access these using the pointer PTR? To access members of a structure instance using a pointer to the structure instance, we use the arrow operator. The arrow operator is the minus sign followed by the greater than symbol. So here the first 4 lines must be clear. So this is basically this is the same thing which we have seen in the last code. Example start PTR is ampersand PTR1. So we are declaring a PTR, we are declaring a pointer to str1. So basically this stores the address of str1. And now to access exint present in str1 using PTR, we use the arrow operator. So PTR arrow exint is identically equivalent to str1.exint. And similarly, PTR arrow exflt is identically equivalent to str1.exflt. Basically, you are accessing the exint and exflt variables present in str1. It serves the same purpose as str1.exint, and you're assigning it to 5 and 8 point as well. And as we have previously discussed, it's possible to have uh, a variable of a user-defined data type inside a structure. And that is what nesting of structures is about. Here, the structure nest has two members, nest int and nest FLT. The structure examples has three variables. First one is an integer variable, second is a float variable, and third is a variable of type nest. Nest is again a variable of user-defined data type. So basically, you are nesting this structure, the nest structure, in the example structure. So how do we access these variables? Once again, let's see. We are declaring instance of example structure, example str1. Basically, you do the same thing to access exint and exflt. You use the dot operator. str1.exint is 5. str1.exflt is 8.2. Now the question is, how do you access the nest int and nest flt present in nest str? You access them by using multiple dots. So first you use str1.neststr to get this one. And then in order to get the nest int and nest flt present in this, use a dot again and you do nest int or nest flt, and you're assigning it to 8 and 4.8 here. So using three dots, if you have another nested structure in the structure nest, you will have you and if you want to access the members of that structure, you'll again have to use a dot followed by the name of that variable, and this keeps continuing. Keep as many dots as you want, I mean, as required. Okay, let's mark your attendance. I'll give you a few minutes. But the attendance form will be deactivated after 5 to 10 minutes. So make sure to mark your attendance within that time. We'll start after a couple of minutes again. Okay, so let's continue. So now let's discuss about the data structure stack. So stack is a data structure in which the insertion and removal of elements happens from the same end, represented as the top of stack. You can literally imagine it as a stack of objects, a stack of coins, or a stack of plates, as in this figure. So basically follows this LIFO principle. So what is this principle? As the name suggests, the element which goes in the last will be the one to come out the first. Basically, why is that? Because when you insert an element into the stack, you insert it at the top. So the last element to go in will be the topmost element. When you remove elements from the stack, you remove them from the top again. So when the top element is again the first element to come out. So basically the last element to go in will be the first element to come out. Or in other words, the order in which elements are removed from the stack is exactly opposite to the order in which elements are inserted into the stack. The process of removing an element is called pop, and the process of inserting element is called push. So stack is a predefined data structure in C++STL. So you don't need to define it. You already have it in the C++STL. So there are certain predefined operations that are provided by the C++STL. So first one is the push operation. You use it to insert an element. Pop, you use it to remove an element. The top function returns the topmost element of the stack. Is empty returns a Boolean value. It returns true if the stack is empty. Otherwise, if the stack is not empty, it has some elements, it returns false. And size function returns the size of the stack. And what is the size of stack? Size of stack is the number of elements present in the stack. So now let's discuss about memory allocation. There are two types of memory allocation, stack allocation and heap allocation. So stack allocation, let's discuss about stack allocation first. In stack allocation, the memory allocation happens on continuous blocks of memory. So like you have a particular block of memory and right on top of that, you have another block of memory without having any space in between. The memory allocation is continuous. There won't be any gaps. The size of stack is fixed and you can't change it. Let's say you have very few memory, we have very few elements in the stack, then there'll be a lot of space left. And if you have too many elements, the stack gets filled and you'll get an error. We shall discuss what that error is later. And all the local variables that we define in functions are stored in the stack. Let's say you have a function main. In that, let's say you declare int x, int y. So basically they are local variables of that function. So where are those variables present? They are present in the stack memory. So every function that you define in your program will have a block of memory. Every function obviously needs memory because it has some variables in it and it has to perform some operations. So where is that memory present? It's present in the stack. And as soon as the function ends, the memory for that function gets erased completely, automatically. So that is why this is also known as temporary memory, because memory keeps getting allocated and deallocated on its own, and it's not really permanent. It doesn't exist as long as your program runs. So that is why it's called temporary memory. So local variables in a function, they exist as long as the function as long as the memory block for the function isn't deallocated, or in other words, they exist as long as the function doesn't return and exit. Because once it returns and exits, uh, all the memory for it gets erased. So all the local variables present in it also get erased, and they will no longer be in existence. So here is an illustration of the stack memory. So let's briefly discuss about this. Now there are two functions in it: add main and of course add mul and of course a main function. So add simply returns a plus b. Mul returns the product of a product of a and b. I could have simply returned a into b, but for the sake of illustration, I'm performing multiplication by adding a b times. So here, what are our variables a and b? They are 5 and 2. Int a equal to 5, b equal to 2. So when the program's control is at this line, this is how your stack looks. Because now at this point, you only have your main function. Main function is the only function that is running at this point of time when the control is here. So you have memory only for the main function. And what are the variables present in main? They are a and b. A is equal to 5, b equal to 2, and sum and pro are still uninitialized. Now, when your program's control comes to the second line of main, int sum equal to add a comma b, the function add gets called. So there'll be memory allocated for add on top of main. So you can clearly see why this is stack. The new memory that's being allocated is being allocated the topmost. So, and what are your variables in add? They are again a and b. So a equal to 5 and b equal to 2. Now, as you can see, this a and b, as we have discussed previously in one of the slides, that this a and this b are different from this a and this b. You can, I guess this diagram will make it more clear. So a and b here and a and b here are different. So they are separate. So any modifications done to this a and b present in the function add won't be reflected in this a and b unless you do it using a pointer. So now the function returns a plus b. Coming to this program again, function returns a plus b. A plus b is here 5 plus 2 7. And now the function exits and all the memory for this gets deallocated. This gets popped out of the stack. The memory for add function gets popped out of the stack. and the returned value a plus b 7 is assigned to sum. So sum now becomes 7 and pro is still uninitialized. Then the control moves to the third line of, and when you go to the third line of main, you call the function mul. So again, again some memory gets allocated for the function main, for the function mul on top of the stack. And what are your variables in stack? A equal to 5, b equal to, you're passing a and b. Ret is 0, I is 1. So these are the variables present in mul at this point. Now the program's control comes to this line, and now it checks this condition. I is 1, b is 2, 1 less than or equal to 2, the condition is true. So it goes into the loop and the function add gets called. So this is how the stack becomes. The memory for add gets allocated on the top of the stack again. So here, um, so when you pass ret and a to add function, ret is 0 and a is 5. So here ret, so just don't confuse with this a and this a. A is basically the first parameter that you pass. B is the second parameter that you pass. Here, the first parameter that you're passing is ret. So and ret is 0. So the first parameter A will be 0. The second parameter that you're passing is A, which is 5. So B, which is the second parameter, which represents the second parameter, becomes 5. Now it returns A plus B, which is 5. And then so basically it returns A plus B, which is 5, and the memory gets deallocated for this. So, and the returned value 5 gets assigned to RET. RET becomes 5 and I gets incremented to 2. I was previously 1, now it becomes 2. Now, the main function. So you basically have the main function and the mul function. Now, again, it checks this condition. After I becomes 2, it checks this condition. And 2 is less than or equal to b, which is 2. So this condition is again true, 2 less than or equal to 2. So it again goes into the loop, calls the function add. So you pass ret and a to add this, add again, and this time ret is 5, a is 5. So the first parameter ret, and which is represented by a. So a will become 5 and b, which represents the second parameter. In this case, the second parameter is also 5. So b is also 5. Now a plus b gets returned. A plus b is 10. And then the function exits, the memory for this gets deallocated, and the returned value 10 gets assigned to RET. So ret becomes 10, and again I gets incremented, I becomes 3. And now it again checks this condition. I is 3 and b is 2, 3 less than or equal to 2 is false. So it exits the loop. It returns RET, RET is 10, so it returns 10. And then after the function mul returns, it basically the memory for it gets deallocated. The returned value 10 is assigned to pro. Pro is 10. Now after this, sum gets printed, sum is 7, then pro gets printed for pro is 10. Then the entire program gets exit, then the entire program is done and it exits. And even the memory for main gets deallocated. So, right. So as we previously discussed, the memory for stack is fixed. You can't vary it. So just can't have as much memory as you want in stack. It's limited. So what happens when you try to use more memory than that? The stack gets overflowed. So this is a very popular error, in fact, and so popular that there is even a very famous website named after it, Stack Overflow. So when we keep calling functions, every function takes some memory At some point, the total memory becomes more than crosses the limit, and that at that point you get this error. This is when you get this error. So what is happening here? There is this function main. It's calling the function fn. Function is a void function. It does not return anything, nor does it accept any parameters. Function has int a in it. So basically, it has some memory in it, 4 bytes. And then it again calls the function fn. This fn will also have an a in it, a different from this, and that will again call an fn. That third fn also calls an fn, and this keeps happening infinitely. At some point, it crosses the memory limit, and you get the stack overflow. Now let's discuss about dynamic memory allocation. This so when you let's say you declare int x equal to 5. So at the compile time, the compiler knows that it has to allocate 4 bytes of memory, but that might not always be the case. You might not know how much memory you need right at the runtime, right at the compile time. So then that is when we use a dynamic memory allocation. So to achieve this, we use a certain operators. So those operators, what they do is they return a pointer. And what does this pointer do? This pointer that they return is a pointer to the first element of the dynamically allocated memory that it allocates. So you can imagine the dynamically allocated memory as an array. The returned pointer is like the name of the array. It's basically a pointer to the first element of the array. So the new operator, this is an operator which we use for dynamic memory allocation. It performs two steps. One, it allocates memory. Second, it calls the appropriate constructor for the construction of object. So don't worry too much if you don't know what a constructor is. Basically, remember that it's a function. The job of the constructor function is to construct the object. This shall be discussed in detail in some of the later sessions. And what does new operator return? As I previously discussed, it returns pointer pointing to the first element of the allocated memory. Basically, this allocated memory is like an array. And what is the syntax of new? It's object type star ptr equal to new object type number of objects. Let's say you want to allocate memory for 10 integers. How do you do it? You write int star ptr equal to new int number of objects. Since you want 10 integers, you write 10 in the brackets. So object type is basically the data type of the memory that you want to allocate. And after we are done using the dynamically allocated memory, it is also important to reallocate it. And we shall soon discuss why it's important to reallocate dynamically allocated memory. And this is done using the operator delete. So what does the delete operator do? It does the exactly opposite thing which the new operator does. It first calls the destructor of the object. Again, destructor shall be discussed in detail later. For now, remember that it's a function. It's a function again. The job of that function is to destroy the object. The job of constructor was to construct. The job of destroyer is to destroy. And then it reallocates the memory. The syntax is very simple. It's just delete ptr. Remember, you can use delete only on those pointers which you have got as a return value of new. Just can't use it on any pointer as you wish. You can only use it on pointers which are the return values of new operator. And then and previously in one of the slides you have seen that then it's important to deallocate memory. Uh, and why is it important? Because dynamically allocated memory exists until you don't call the operator delete. Let's say don't call delete at all. It exists throughout your program. So once you're done using it, if you don't call the operator delete, you're basically wasting that space. You're not using it, nor is it available to other operations. So it's important to call the delete function. Now I have a question. So so the dynamic, so we've previously seen about the stack memory. So the dynamically allocated memory, is it present in the stack or not? Yes or no? So I'll give a 2 minutes of time and later the polling shall be closed. Okay, so uh, I'll close the polling and the correct answer is no. So see here, look at this point. Dynamically allocated memory exists as long as delete is not called. So if you don't call delete, it will exist all throughout the runtime of the program. Basically, it is permanent. Had it been present in the stack, it would not have been permanent because memory in stack is temporary. So it is not present in the stack. Then where is it present? It is present in the heap. So this is where the dynamic memory allocation happens. Every time we request for some chunk of memory, it gets allocated from random parts of the heap. Now this is an illustration of the heap. Just don't mind about these names. They are just some random names. So this cloud represents the heap memory, and these white colored circles are the memory allocations that we have done in the heap. So as you can see in the stack, our memory allocation was continuous. So one block of memory was above the other block. There were basically no gaps in between, but that is not the case here. These objects are present at random parts of the tree, but these individual objects, say this duck object, this is continuous. There are no gaps within the duck objects. So the memory chunk that we request, in this case, the duck object will be continuous, but that continuous chunk of memory will be present at random location in the heap. And this is called heap because it is just a file of memory available to programmer to allocate and deallocate. And now memory leaks. Since the heap memory doesn't get deallocated automatically, which is not the case with a stack, in stack it gets deallocated automatically. We need to explicitly deallocate it. And if you don't do this, the memory keeps growing and finally the heap becomes fragmented. This is known as heap fragmentation. Now let me explain it using this diagram. Let's say you have many such white colored objects. Just imagine how this cloud looks. This blue color space is basically the empty space available where you can further allocate objects. Now imagine you have some 50 such objects, or too many objects. Now you'll have a few patches of blue left here and there. Now, if you put together all the patches of blue, and now let's say you request for another portion, another chunk of memory now, after having a lot of memory allocated already. Now, though the total sum of blue area is might be greater than your requested memory, but it might be possible that it won't be allocated. Why won't be allocated? Because no single patch of blue will be large enough to accommodate your memory request. So the sum of total blue patch, the total area of total blue area might still be greater than your requested memory, but no individual patch of memory will be big enough to accommodate your memory request. And that is when the memory allocation fails, and this state is called the heap. This state is called the fragmented state. The heap gets fragmented. This might also lead to security vulnerabilities because your data is still there and it can be accessed from any part of the program. You just need to have the pointer to the uh, dynamically allocated memory. If you have that, you can access it anywhere, anytime because it's present throughout the program if you don't deallocate it. This is another question. Um, so basically we have seen that the new operator returns a pointer. So it allocates memory in the heap and it returns a pointer. So now where is this returned pointer present? Is it present in the stack or in the heap? I'll again give it 2 minutes. You can start. If I'm closing the poll, the correct answer is stack. So let me illustrate this with the diagram. So this cloud is the heat. Now these two don't care about the names. They are just two chunks of memory that you have allocated. And now these dots represent the pointers which your new operator has returned. So these pointers and this cloud is the heap, this is the stack. So as you can see, these pointers are present in the stack. They are present in the stack and they point to memory locations in the heap. So that's it for this session. So please share your feedback by scanning this QR code. Uh, I'll wait for a few minutes. Okay, fine. Hope you all enjoyed this session. So ending the meet.